Okay, this time we're going to talk about integer exponents. So let's get down to it. Integer means we can include the negatives, so let's focus on the non-positive exponents. So z is a non-zero complex number, n is a positive integer. Notice I'm not just using real numbers. Real numbers are great, but we need to understand beyond just real numbers. So if n is a non-zero complex number, n is a positive integer, well, we have this nice property. So again, I'm stating n as a positive integer. So I'm going to state some definitions. One, that z to the power of 0 is equal to 1. Now, there's a lot of reasons how you could explain this, and we'll kind of talk about maybe some of them in a minute. Now we're saying n is still positive, but we have a negative positive number. The reason I'm doing this particular way is to actually justify that the negative out front is not the number. The negative is attached to whatever is put in its place. In this case, my positive number, my positive integer n, right? So that's what's put here. And we define that as 1 over z to the n. So how could we demonstrate to a student why z to the power of 0 equals 1? Well, there's a few ways to do this. One way is to look at the properties of powers. If I continually decrease something, so if I start with n to the power of maybe 4, and then I divide it divided by n, I'm going to have n to the power 3 divided by n. Again, n is my base. I'm going to get n squared divided by n. I'm going to get n. And then if I divide this by n, well, I get 1. Now this absolutely does lead into the other properties, right? So this would be n to the negative 1. This would be n to the negative 2. In each case, this is a division by n as I move down. So that is a nice way to explain why we get 1. Are there other ways? Absolutely, there are other ways. I want you to consider how you would explain this to a student. Why is it true? What justifies it? Maybe what justifies it in your own mind. And then maybe that'll help you have a good, solid understanding to explain it to students. How could you demonstrate to a student why z to the negative n is 1 over z to the n? I kind of just did that. The choice of how I explain it most of the time is because that's how students recognize it. And just as I explained the previous of getting to 0, anything to 0 power is equal to 1, this also helps me explain the negatives. And they kind of go hand in hand. Let's look at properties of exponents. So we've been given those statements. And if we look at a case where z to the a times z to the b, and we say it's equal to z to the a plus b. So if we're given the case that a is a number greater than 0 and b is a number greater than 0, and we in the last section kind of showed that this is true. If we use a special case that a is less than or equal to 0 and b is greater than or equal to 0, we can create a rule for z to the power of negative b. Now, to prove that case in general with different values of a and b, This would be a cases, right? If we were doing this, we would do cases. So we're not going to do this one. I'm not going to do the multiplication. I'm going to do the division. So I'm going to look at the quotient rule, z to the power of a divided by z to the power of b, and I'm saying that's defined by z to the power of a minus b. But I need to look at cases. So suppose a equals b. Well, then z to the power of a over b is equal to z to the power of a over a, which is equal to 1, which we know that 1 is also equal to z to the power of 0. And z to the power of 0, again, I'm using this piece. I used it here to make that jump between these two for this to go there. And I'm using it again, z to the power of a, or z to the power of 0 is z to the power of a minus a. But I'm also going to now use the same property to replace this a with that b. So here's where they would, if they're the same, this would be that simple case. And then let's look at another case. Let's say we have z to the power of a minus b, and we're going to suppose that a is greater than b this time. We looked at when they're equal, so let's consider that a is larger than b. Since a and b are whole numbers, a is equal to b plus some n for some other whole number, right? So n is just some other whole number. That means that z to the power of a divided by z to the power of b, I can replace what a equals, right? I can replace this here with b plus n. So then I have b plus n minus b, right? So this piece would come out and be z to the power of b plus n minus b, which is going to just equal n, some other whole number. Since a is equal to b plus n is equal to a minus b, so z to the a minus b, right? So that's taking this piece and going here, which goes back to here, which is equal to what we started with. Success, right? But then I've looked at when they're equal, I've looked at when a is greater than b, so I need to look at when b is greater than a. Same idea. A is less than b this time, and since a and b are whole numbers, I'm going to say b is equal to a plus n. Same idea, I'm replacing it. So in this case, right, this piece kind of comes out as z to the power of a minus a plus n. That distributes, so z to the power of a minus n, and we can see that that is going to just be z to the power of negative n, which gave us this property, these two. And reversing this z to the power of negative n, this is the same as saying n is this piece, right? So I can kind of go right to there, which gets me over to here. So these are just manipulative of algebra, not anything real fancy. Other properties. The other properties of exponents can be proven for zero exponents, negative exponents, by breaking things into cases in a similar way. So in the text we explored, so if you've read the book, we explored, and in the last question, f of x equals x to the power of n, where n is just a positive integer. And we now recall the graphs for the negative integers. So we need to, by hand, consider these. I'm not asking for something crazy, but I am asking that you consider these and do these. So let's consider these. What does it look like? And A, I can probably answer on this page, but I'll probably need the other page for the other. Okay, so let's consider x to the negative 1. So x to the negative 1 power. What does that look like? Well, in simple, right, let's do this in black. And then turn that off. Oops, that didn't do what I wanted it to do. Okay. And then this is going to be, so if I plug in a negative value, kind of considering what's going to happen, this is going to graph something that looks like that. Right? And it might be sloped a little bit more than that, but that's in general what we're looking at. And then let's consider what happens when we talk about x to the power of negative 2. Again, same idea. I'm going to go ahead and put a, in this case, well, this is still even though it's going to be, right, this is going to be 1 over x squared, just like this was 1 over x. So this one is going to stay up here. Right, I can't plug in 0, that's still an asymptote. And the more I put in there, the more that x becomes, it gets closer and closer to 0, the larger it becomes. The closer it becomes to 0, the more it drives it up. So, but it's never going to be a negative value. That's never going to be a negative value. Whereas this will become a negative value, right? And we can see that if I look at, all right, with x to the negative 3, and this is x to the negative 3, we really expect kind of the same thing. A little bit tighter, right, because it happens a little bit faster. Not quite as sharp as I just drew that, but I'm doing it rough sketches. You could choose a point. I would genuinely choose something easy like 1, right, -1 in each case to kind of plot that 1 point, and then I would do the maybe 2, right, to see how that relates, and -2. Same idea here. We're expecting to see, because this is x to the -4, right, so we're kind of expecting this pattern to continue, and it will. That was way looser than it probably would be, but you get the idea, right? So by hand, you're going to graph these. It specifically says graph. That means you have to draw a graph. And it specifically says by hand. You get to use all non-zero real numbers as your domain. You do not have to, it doesn't have to be perfect by any means. You can't even list all non-zero real numbers. So, no. But I do expect some points. And other than that, you're good. Check your answer using a graphing calculator or computer software. My suggestion is usually Desmos. One, because I think you guys should all have an account. It's free. And you should save certain things so you can go back and use them in the classroom when you're teaching, right? So some of these you may want to keep if you end up teaching this sort of class. All right, what's the next thing? Consider the function f of x, xn, where n is a negative integer. Make a conjecture on the values of x of the limit of x as it approaches infinity for x of n, the limit of x as it approaches negative infinity for x of n, limit of x as it approaches 0 from the positive of x of n, and the limit of x approaching 0 from the negative of x of n. All right, so we'll do that on another page. Oops, come on. Come on. Take me to the next page. Come on. Dang it. That's not what I want. Okay. Come on. I am writing that whole thing up. Okay, so now we're looking at limits. This is part C. Let's see, what is this? Part C. Okay. So we're looking at f of x equal to x of n, specifically where n is an element of the negative integers, right? So we're having to think about, well, what's going to happen? Well, as limit as x approaches infinity, what should be happening of x of n? Well, this means n is getting a bigger and bigger infinity, right? We're going to a bigger and bigger value. This is going to go to 0, right? Because it's a negative infinity, right? So the idea is, well, this is going to become a larger denominator. And it's always over 1, so that's getting closer and closer to 0. So that part's pretty straightforward. When we think about the limit of x approaching negative infinity, right? Negative infinity of x of n. Well, this is also going to go to 0, right? Just because it's a larger negative value, it's still a larger number on the denominator. So this applies to both of these, right? This idea applies to both of these. The next place we got to look at is the limit as x approaches infinity, or approaches 0 from the positive side. We can't plug in 0. 0 ends up in the denominator. No good. Undefined. So let's look at as we get closer and closer to 0. Well, as we get closer and closer to 0, we get a smaller number in the denominator. This is smaller than 1. So 1 over a smaller number is going to go to infinity. Okay? It just is. It's going to go to infinity from the right-hand side. So this is going to equal infinity. Now, this piece is where things kind of change up a little bit. Not a lot. X is approaching 0 from the left, or from the negative side. So x to the n. This rule is still applying. This rule is still applying. The question becomes, do we end up with a negative number? So this actually does this nice rotation or harmonicness to it, and it becomes positive or negative infinity based on the n. So this is based on the n. If n is even, then it's going to go to positive infinity. If n is odd, it's going to go to negative infinity. So there is a little difference there. What was the next question? What is the range of this? Okay, so let's consider this range. Here we have A, B, C, D. So what's the range? The range, well, range of f of x equal to x of n. N is a negative integer. Then we get from negative infinity, right? Our outputs will actually depend on n. So I guess, let's see. Let's do it like this. Let's not use this. Then if n is even, if n is even, we get 0 to infinity. If n is odd, we get negative infinity to 0, union 0 to infinity, right? We still can't be 0. 0 won't work. What was E? E was, how does this exercise help in understanding why 0 to the n is not defined if n is a negative integer? Well, okay. So some pretty straightforward stuff you guys already should have a firm grasp on. And that is this. For E. 0 to the n, if n is positive, right? So if n is a positive integer, then 0 to the n is equal to 0 times 0 times 0 times 1, 2, 3 times 0, right? N times, which is equal to 0. If n is in the negative integers, then 0 to the n is equal to 1 over 0 to the n negative n, right, because n is negative, which is undefined. Right, so stuff you know, we're just justifying it. What was the next question? We're going to consider mathematical and notational issues that arise from negative exponents. So what do we got? Write 7 plus square root of 2 to the negative 1 as a fraction, then try to write it in the form of a plus b to the square root of 2, where a and b are rational. Yes, and then it even tells you that you may have learned this procedure under the name rationalizing the denominator. It's something you guys like to do. Mathematically, the math doesn't care. Okay, so first write it as a fraction. That's the easy part. Then rationalize it. Okay. So let's see what kind of room we have here. I think we have enough room maybe to do this. Let's kind of do this and that. Okay. So A, right, for new question. This is, what was that? Question number 2? Number 2. I don't remember the number actually. Oops, I didn't want to jump pages yet. I think we can fit this in. Let's fit this in. So we're dealing with 7 plus square root 2 to the negative 1, which is 1 over 7 plus square root 2. So why do we rationalize? Actually, there's no good reason. Well, that's not true. It's an exercise. It helps you learn to manipulate equations. It helps you understand conjugation. Yes, all of these things are true, and that is really why you do it. Not necessarily that the math cares one way or the other. Mathematics is beautiful that way. 7 minus square root of 2 over 7 minus square root of 2. So basically I'm going to times it by 1. So 1 over 7 plus square root of 2 times 1 is equal to, right, because that's all I'm multiplying it by. I'm multiplying it by 1. So I can have a new way to write it. So what do I have? Well, I have 7 plus square root of 2 over 7 times 7 is 49. And then I have square root of 2 times square root of 2 negative 2. So this gives me 7/47 plus, right, plus a, negative, right, it'd be, oops, this is not a plus. Sign error. This is a subtraction. So this is not a plus. It's a subtraction. That'd be 1. Yeah, it'd just be 1 over 47 square root 2. So in this case, given what they told me, A is equal to 7 over 47. That doesn't simplify. And B is equal to negative 1 over 47. That also doesn't simplify. And this is in the form A plus B square root 2 that they had said they wanted it. Pretty straightforward. How do we do B? B is 7 plus square root 2 squared. Nope, negative squared. which is going to equal, let's maybe go down here, 1 over 7 plus square root 2 squared, right? So I have to deal with that. So let's deal with that. So this is going to be 1 over 7 times 7, 49. 7 square root 2 plus another 7 square root 2 is going to be plus 14 square root 2's. And then square root of 2 times square root of 2, both positive, is going to be plus 2. Cleaning that up a bit, right? Because that's kind of the goal here. 51 plus 14 square root 2 all over 1. This right here is equal to all of that. But we want to rationalize the denominator. So that means we got to times this by 1. But our 1 is going to look like 51 minus 14 square root 2 over 51 minus 14 square root 2. Who doesn't love these big numbers? Yeah. Okay, so the top part's easy. Let's do the top part. 51 minus 14 square root 2. That's beautiful. 51 times 51. What is 51 times 51? 51 times 51 is 1 times 1, 2601. Okay, that was without a calculator, so please don't quote me on that. And then, well, then 14 times 14, negative 14 times 14 times 2, 392. Cleaning this up. This piece, 2209. Okay, now this becomes 51 over 2209 minus, right, 14 over 2209 times square root 2. So A is equal to 51 over 2,209, and B is equal to negative 14 2,209. Awesome. All right, so now we need to look at, that's some fun calculation, right? If you were bored and you wanted some calculation to do, this is some fun stuff. Doesn't take a ton of time. Do be careful. Maybe a calculator, 51 times 51, like I'm pretty sure that's right. And I'm pretty sure 14 times 14 times 2 is that. But don't quote me. Double check, right? Always double check. What is C? C is now we're doing C, part C. This is 4 plus, this is kind of fun, 13i, right? Because who doesn't love this? This is going to be 1 over 4 plus 13i. This is why we do math, because this is the fun part, right? I think so. Times 4 minus 13i over 4 minus 13i. So we've got to multiply by 1, and we'll clean it all up. What do we get? We're going to clean this up, and we're going to get 4 minus 13i, I being the complex number, and then 4 times 4 is 16. 13 times 13 is negative 169 I squareds, which we know that I squared is equal to negative 1. So this becomes 4 minus 13i over 16. Negative 1 times plus 169. So 5 2's no, 13 no. Got it. Okay. So this becomes 4 over 185 minus 13 over 185 I. In this case, A, right? A is equal to 485. B is equal to negative 1385, right? So that's that. D, I'm going to let you do on your own. I mean, I don't want to take away all your fun knowing the answers. D is 4 plus 13i to the negative 2. So you're basically going to do 1 over 4 plus 13i squared. And then you'll have another version with I that you'll have to do the conjugate. And then you have to answer E. E, you're using words, right? You're giving me a sentence that says something like, I don't know, maybe in both parts, A and D, we see that both A and B are in the rational numbers in each one of these cases, with the irrational part attached to the B. Hence, they're both similar, or something to that effect. All right. I think that's a good place to start, and keep working at it. Have a good day.